is going on page 33. When we're done, we're going to talk about differentiability. So let's talk about some words. Differentiability is being differentiable, which goes along with differentiation, which all has to do with derivatives. So derivative and differentiable, they sound different, and they're obviously not forms of the same word. But if something is differentiable, then you can find the derivative. So those things they all go together. Right? So it says earlier we discussed the definition of continuity. So a function f of x is said to be continuous at, and I think, because I was just looking at the piece of paper, yours has, I think at and x got like drawn on top of each other or printed on top of each other. Yeah, so it should say at x equals c. Okay. So we know a couple of things that are true, right? It is continuous if the limit as x approaches c from the left of f of x equals what? The limit as x approaches c from where? The right. Okay, so the limit from the left, that's from the left, equals the limit from the right, which means that the limit exists, right? Then we know that the second thing that has to happen is f of c exists, right? Exists. Okay, can't spell. Exists. There you go. And then what's the third thing? They're equal, exactly. Then we can say the limit as x approaches c in general, like I don't have to put the left and the right, just c, because that means that those two have to be the same, of f of x equals f of c. Okay, so if it is continuous, continuity and differentiability are connected. They are not the same thing. One doesn't always guarantee the other, but the other way around it does. So let's just look at this. So remember, if you can draw the graph of f of x without picking up your pencil, it's continuous, right? That's how you get your continuity. Okay. So when we talk about something being differentiable, then differentiability is simply saying that the saying that the derivative, well, I was going to write it that different. Saying that the, hang on, I changed the words. No, I can't get the words in there. How do I, differentiability is saying that the blank of the blank. The derivative of f as x approaches c exists. Okay. Differentiability is simply saying that. Sorry, I have a different version of these in my word. You know, if you don't make these yourself, sorry, I look like an idiot right now. If you don't make these yourself, then what goes in the blanks and the way the sentence is structured differently, you can't come up with it. I know what differentiability means, just so you know. It's simply saying that the, here, we're just going to mark all that out. We're going to say it differently. I don't like those words. Saying that f prime of x, the derivative, exists. That's what we're going for. If it is differentiable, then the derivative exists. That's what we are trying to get out there. Okay? So there are two rules that must be true for the function to be differentiable. First one is f of x must be continuous. At x equals c. So it doesn't have to be continuous like for the entire function, but where you're trying to get it to be differentiable, it has to be continuous. Okay? And then number 2, the derivative from left and right are equal. Okay. So same kind of thing as like we look to see if they were the limits from the left and the right are continuous, and then we're going to look to see if the derivative from the left and the right as x approaches c are going to be the same. So continuous, and then we look at the derivatives from the left and the right as well. Okay? So what would some examples graphically be that it would break the second rule of differentiability? Okay, so if we have any discontinuities, right? Or if I have a sharp turn, which can be called a cusp, but you don't have to be fancy about it. I'm just going to tell you that that's what it's called. Or if you have a vertical tangent. So tell me, the derivative of a function, what does it tell you about the function? The slope at that point, right? So it's the rate of change of that function at that point. So if I have a discontinuity like I do right here at -2, see that discontinuity right there? Then it's not differentiable at that point because there's a discontinuity. Doesn't mean it's not differentiable at -3, but it's not differentiable at -2 because I have a discontinuity there. Does that make sense? The sharp turn that we're talking about, because I can't get the rate of change at that point if the point doesn't exist, right? So the sharp turn or the cusp will be like what's happening right here. Because if the derivative is the slope from the left and the slope from the right are not approaching the same thing, right? They're just completely different because I just turn really quickly. So this right here, this is a negative slope, this is a positive slope. They're not approaching the same thing from either side, okay? So that's why it doesn't work at a sharp turn. Another discontinuity would be our jump right here, right? And then if we talk about a vertical tangent, so remember our tangent lines, like I could draw, I'm going to erase all this so you may not want to draw it, but I can draw my little tangent lines like this along the way. If I draw one right here, it's a vertical tangent. Well, what's the slope of a vertical line? Undefined. So you can't approach undefined. Does that make sense to you? So like these slopes right here, these are negative, okay? And they're getting more and more negative, basically approaching negative infinity. These are positive and kind of approaching positive infinity. So they're not approaching the same thing. So that's why the vertical tangent doesn't work there. Okay, let me erase these so we can look back at the other stuff. All right. So those are the three things: discontinuity, sharp turns or cusps, and vertical tangents. So when we look at this, it says, find all the values of x. So we're not really looking for ordered pairs or anything. The values of x where the function f of x above is not continuous. Okay, so it's just asking us about continuity here. So I'm not continuous, I would say right here. Would you agree with that? So I have x equals -2. And what type of continuity is that? Removable. Okay. So then if I put my pencil back down and it's all continuous till it gets to here, right? And then what kind of discontinuity is that? Jump. So then that is x equals 5, and that is jump, which is also a non-removable type of discontinuity, right? We got removable and non-removable, more specifically jump. Okay, we good with all that? Then it asks us to find all the values of x where the function f of x above is not differentiable, right? So it's not differentiable here for sure, right? Would you all agree with that? So because we have continuity, so we can say x equals -2 and 5, and that is because of discontinuity. then I would say it's also not differentiable here, right? Because we have a sharp turn. You agree with that? Here, we have a sharp turn. And here, we have a sharp turn, right? So then I can also say it's at x equals -9, -6, and 2. And my reason can be sharp. Sharp turn is fine. I don't know, and it's funny. That's fine. You don't have to use the word cusp, but other things, if you don't explain with the right words, then it's not okay. But this is one of those that's okay. Probably just because we don't want you to be confused, just because of a vocabulary word. And then, is there anywhere else you think? Right here? Yeah, it's 7 because we have a what? Vertical tangent. X equals 7. We have a vertical tangent. Okay with that? Any questions on that? Okay. So let's flip this over. All right, so it says consider the function g of x. G of x is not labeled, so we label it g of x. Because we're about to start getting functions where we may be talking about g of x, but then our graph might be of g prime of x, right? The derivative, the g prime, or vice versa. Or we're talking about g and they give us a graph of h or something like that. So you got to make sure you're paying attention to what's actually being given to you, right? So I want g of -4. Is that something I get to just pull off of my graph? What do you think? Yes? So 1, 2, 3, 4. So g of -4 is right there, but I don't get to just guess at what it is, right? How could I figure out exactly what that is? Is that 1? It's hard for me to tell. What could help me make sure I figured it out correctly? I mean, I don't have a function that I can't substitute. The slope, yeah? The slope of this line segment right here, right? So that slope is negative, not that that would necessarily matter. But between -2 and -6, I went to the left 4. I could go to the left 4 here and then go up 2, right? So if I'm here at 1, 2, 3, 4, how far did I go up? When I go to the left 4, I go up 2. So if I go from here to the left 2, I go up 1. And so then I do think it's 1, and I'm not guessing off my graph. Make sure you're using your slope to figure those things out, okay? Does that make sense to you? All right. I mean, if it's on a grid, that's different, but I don't really have a grid. I'm kind of, you know. All right, so then I'm asked for g prime of -4. So that's different. G prime of -4, what does the derivative give me? What does the derivative tell me? The what? The slope. Can I find the slope at this point? Yes, because it's a constant slope, right? So is this slope positive or negative? Negative. So, and it's a negative what? 1/2. Because your rise is 2 and your run is 4, and you know it's negative, so it is 1/2. Okay? It's just the slope of that line is all we're asking. Okay, we're good with that? You sure? Okay. All right, then g of 3. Well, what's g of 3? 2. Do I have to think real hard? No, because it literally gave it to me, right? What about g prime of 2? What do you think about that? Does not exist. Not differentiable. Since it's not differentiable, the value does not exist, right? So do I put an equal sign? No, because we can't equals does not exist. It just does not exist. Okay, we good with that? All right, so I'm going to give you a couple minutes. I want you to do, or a minute or so, I want you to do the next 4. You can just talk amongst yourselves at your table. All right. Are we ready to talk about them? All right, g of negative 2, do I get to pull that right off the graph? Yes, g of negative 2 is what? 0. All right, g prime of negative 2. So if I'm going to have a value, then that means this has to be differentiable. Is it differentiable right here? No. So my answer is does not exist. Because basically I can't find a slope there, right? Then what about g prime of 2? Does not exist. That's another sharp turn there, right? Good. And then g prime of 4, right there, does that exist? Yes, so now I can put my equal sign. What is the slope right there? Negative 1. Good. All right. What questions you got? Okay. So from a g graph, we can find g prime. When we look at this next one, this is another time where I don't know why that stays there. Sometimes it does, sometimes I think if I do this and I go back, then it'll go, it's like magic. Yeah, then it sticks, I don't know. All right, so here I have the graph of h prime. It tells me it's h prime, it's labeled as h prime. So this is the graph of the derivative of a function, okay? From this graph, I can obviously find derivative values. I cannot actually find h values without more information. Okay, but notice what we're asked for here. Let's just do h of negative 1. So h of negative 1, here's negative 1. I'm sorry, not h prime of negative 1. What is h prime of negative 1? 3. We agree with that? Okay. So it doesn't ask me for the, actually it asks me for this on I. So let's talk about I. I was going to make you do it right here, but so we just did A, now we're going to look at I. I asks for h double prime of negative 1. So what do you think the double prime, what do you think that means? It's the slope of this. So h prime is the derivative of h, right? This is the derivative of h prime. So if what I have is h prime, then h double prime is going to be the slope of that one. Does that make sense to you? So the slope, when x is negative 1, what's the slope of that tangent line? 0. Okay, that makes sense to you? All right, so then I'm going to give you a couple minutes. I want you to come up with all of these together at your table. Okay, so let me clarify something about a question I just had was, when we did I, why did I use the tangent line? Because the derivative of the derivative right here, so your second derivative here, that means we are finding the rate of change at a given point. Now up here, when we found the rate of change at these given points, those points were on line segments, so I was able to just find the slope as we understand slope of lines. However, when I have a curve, I can't, to find the slope of the curve, I actually want the slope of the tangent line at that point, so that's why I drew in that tangent line and why I found that slope. Okay, is everybody okay on that? Because that was a good question and I wasn't very clear on that. All right, so let's look through the rest of these. We have, so h prime of 1, that means that's something I could maybe get off the graph. Like I don't have to think about slopes and stuff because this is an h prime graph, so you want to pay attention to what your graph says. So at 1, my answer is 1. We agree with that? Okay. H prime of 2, what's my answer? D and E. Does not exist, or undefined is okay too. Either way is fine, but D and E is shorter to write than undefined, I guess. H prime, so again, I can just get it straight off the graph. H prime of 4, now there was a little discussion over there about, am I safe to just kind of assume that it's 1/2? We should never assume anything, right? But how do I figure out that for sure it's 1/2? Using what? The slope. So the slope of this line segment, to go from here to here, I'd go up 3 and over 2. So if I'm only going to go over 1 instead of going up 3, I go up 1.5. That tells me that it's a half up from 0, and that's where I get 1/2 from. Okay? We good on that? It was a very good discussion over there, too. All right, so h prime of negative 5. So I've got to remind myself, I don't need the slope at negative 5, I just need the value. So at negative 5, again, I've got a number that's not a whole number, but I can see my slope. I would go up 1 and to the left 4. So if I just go to the left 2, that means I've gone up 1/2. So 3/2. Do you agree with that? Or 1.5. I mean, you could put 1.5, but it kind of makes my skin crawl because I'm afraid that y'all are going to do weird things with the mixed numbers, and we're not cooking. That's right. All right, so h prime of -5. So I found h prime. I want h double prime now. So we just talked about the slope. I would always, well, what I always do and I suggest you do is the first thing I ask myself is when I'm looking at it, because this is so easy to do and so easy to mess up, is this slope positive or negative? Negative. So I'm going to put my negative sign on there first so I don't mess that up, right? And then I know that I go up 1 and over 4, so -1/4. Okay? Because the last thing you want to do is get something simple like slope wrong just because you missed the sign, which again is very easy to do. All right, h prime, I can get it straight off my graph of -3. That answer is 1, right? H double prime, which is the second derivative, that means it's the slope of the slope type of thing. So at -3, prime graph, can I do that? No, because it's not differentiable. Why? Sharp turn. So this is D, N, E. Okay, we okay with that? You've lost your passion about math. You're over there playing tic-tac-toe like children. Stop it. All right, so then we did I. Here's J. H double prime of 4. So here I am at 4. H prime is my graph, so I need this slope, which we really have already talked about. First of all, is that slope positive or negative? Positive, so I don't have to worry about a sign. And then I know that I go up 3 and over 2. So that's 3/2. H double prime of 2. What do you think about that? Doesn't exist. If the point doesn't exist, then it can't be differentiable at that point, right? Your discontinuity, it's not differentiable. Therefore, I cannot find the derivative of it. So this does not exist. And then what about H double? Do you know exactly where 1.17 is? No, but it's in here somewhere, right? Can we find that? Yes, that's the slope. Is that slope positive or negative? Negative. And then what? We go 2 and 2, so that's 1. You agree with that? Would it be okay on a free response part of an AP exam to put -2 over 2? Yes. I mean, -1 makes more sense, but that's okay because it's a safe stop type of thing. Okay, we good on all that? Okay, grab the little half sheet of paper I put on your table. This is just kind of restating what we've already talked about, but I like the way some of this is said because I said this the other day, but you can't always go one way and the other, back and forth. But this gives you the definition of differentiability again, right? So a function is differentiable if f of x is continuous at c, f of x has no sharp turns or cusp, left limit is equal to the right limit, and it doesn't have an asymptote or vertical tangent. So the vertical tangent part, the asymptote part, really goes along with the continuity. So it's really, the third thing is really more your vertical tangent that you can't have. Obviously, the asymptote is a problem as well, vertical asymptote, but the left limit has to equal the right limit type of thing. All right, so here's the important thing and why I wanted you to, and on this, you can put this on the same page, but you can just kind of type this flat and then, put the little thing on top of it. But differentiability applies continuity. So anytime you see the word differentiability, you write continuous above it. But just because it's continuous does not mean that it's differentiable. It can be, it opens the door, but it doesn't guarantee it. But when you are explaining things, if something says the blob f of x is differentiable at whatever, then you can say f of x is continuous because it's differentiable, like we know that for sure, okay? And so here's some little tidbits to kind of explain it a little bit different, okay? And again, continuity is usually defined over a closed interval. Differentiability is over an open interval. We'll talk about that more when we look at some notation, but this just kind of gives you some, what I think is good information there. Okay, we good? Awesome.